This video is going to cover sampling, so mostly just the different types of sampling. I have another video on calculating a required sample size, if that's what you're looking for. So basically, populations are typically pretty large. Like, let's picture like an entire city that has like 100,000 people. If we were to try and involve everyone in whatever we're trying to do, like whatever if we're trying to measure disease or establish some or do some study, basically, if we were to include literally everyone in the city, that would be what we call a census. It's often more efficient to sample the population. So basically, taking like a random subset represented by this circle. The circle is like more of a metaphor just because like the way it's written, it's non-random in the sense that like all these people are related physically, geographically. But this is more just like a conceptual idea that we're just drawing a circle around the population and taking a subset of everyone who's actually there. And yeah, so that's who we'd keep. And yeah, for our purposes, that's just a smaller subset of the whole population. So ideally, our sample is smaller because then that's the only way we can. That's how it represents a more efficient strategy, is that it's smaller than measuring everyone. Also, we want it to be representative of the entire population. So here's some definitions just before we get started. So the source population is the population from which the sample is drawn. So like that whole town I was talking about. The sample is those who are ultimately sampled, so those who are ultimately chosen. The sampling unit is the unit that is sampled. That's kind of self-explanatory, but also so in my previous example, you might be choosing individuals from a city. It's also possible you might have been sampling houses. So the unit is what is sampled from the source population. And the sampling frame is like a list of units that you're able to apply a random selection process to. So like some kind of registry that lists everyone who's living in a town. Or if you're using hospital records, just like a list of everyone who was in the hospital at a given time. Probability sampling is the basis of most sampling methods that are used, and with that, every member has a non-zero probability of being selected. Doesn't necessarily have to be the same probability of being selected, but basically, like everyone in your population, it's possible for them to be selected, and the probability of selection is typically known. So ideally, it's a random sample where you're choosing who is involved. But if you just rely on volunteers and kind of anticipate that to be random, you run into some problems just because people who volunteer for studies might be more health conscious than people who don't volunteer for studies. So simple random sampling is a very common way of sampling a population. So basically, you obtain that sampling frame, that list of everyone who lives in the town, and basically everyone in the town has the same probability of being included, and you just randomly pick people from the town through some formal process, like assigning everyone in the town a number, and then like randomly drawing those numbers out of a physical like hat or something. There's definitely more official methods, but like conceptually, that's what we're trying to do. It requires that you have the list of everyone available, which isn't always possible. With certain populations are kind of in flux, like a hospital population over time. Sometimes it can be difficult to obtain a complete list of everyone who is there. And yeah, certain groups can end up underrepresented. Say if it's like a community that has an age structure where there's not a ton of old people, it's possible that by chance no old people will end up in the sample. And although old people are underrepresented in that population in general, having 0 old people in our sample is still not representative. To have a couple old people in the sample is more representative of what that population is like, rather than no old people. Systematic random sampling is choosing every nth subject in their order of appearance. So a common example of that is like every 8th individual admitted to a hospital. And yeah, this is a good one because first of all, it assumes random order, and it avoids the impact of trends over calendar time. So, like for example, if we were to just pick everyone in the everyone who comes into the hospital on a given day, You might end up with people who are there for the same reason, such as like a multi-car pileup. A lot of people coming in are coming in for the same reason, like the same event. Also, let's just say it's like January 1st. You're going to get a lot of people coming in on that day just from various mishaps from the night before, from New Year's. So basically, doing this strategy over like a long period of time, you're able to both account for variation over a day in why people are going to the hospital and variation over calendar days. And yeah, it doesn't require a sampling frame, which is nice. You don't need a list of everyone who's going to come into the hospital. You basically just need to ask every eighth person. Cluster sampling is a situation where before the unit was an individual, so picking an individual from a list of people in a town. Cluster sampling is when basically the sampling unit is clusters. An example of a cluster is like, let's just say these are all households in a town, basically, where each household has multiple people living there. Or it could be classrooms in a school, where each of these classrooms is composed of several children. So now when we sample, drawing a circle before just to represent picking a random combination of them, we basically keep everyone in that cluster and then sample every individual. And note that sometimes the individual is still our unit of interest. It's not the cluster, where we used cluster sampling to get people. So basically, like, we had this school and we picked like 1, 2, 3, 4, 5, 6. We picked like 7 classrooms, and then we sampled every child in that classroom. We're not looking at how classrooms differ. We're looking at how people differ. But basically, we use cluster sampling to arrive at that. That becomes very efficient if these places were separated by very large geography, like separate towns. We're having someone go to every town just to sample one person who is chosen. That wouldn't make sense. You would cluster sample a town and then sample everyone there in or cluster sample a school or classroom. It just involves less traveling because you get to sample way more people at one place instead of having to do like one person from several places. But you need to be careful because there's an effect of clustering now that you've done cluster sampling, where if this is like a household, these individuals are more related than the general population, like literally, genetically. If it's a classroom, they share several influences, like probably geography, depending on if there's several schools. Also within the classroom itself, they're all under the influence of the same teacher, and that might influence various things. So you need to account for clustering, and I'm going to do a video on clustering at some point. Multi-stage sampling is pretty cool. It basically applies what I just talked about, I guess, like more of a simple random sample or a cluster sample, depending on what you want. But basically, you're doing multiple sampling stages where you have a primary source population that you sample from, like a town, and then you have subunits that you would sample from, like neighborhoods within those chosen towns. So just to illustrate that, let's just say we have cities in Ontario, like a list of all of them, and the sampling unit is a city, and we basically, our sample is composed of randomly chosen cities. So let's say these are the chosen cities. And then we have our second stage, where basically now only the cities that were chosen in stage 1 are part of this now. All these other cities are disregarded. But within these cities, let's just say we sample apartment buildings randomly. And that's our unit, and our sample is the randomly chosen apartment buildings, so one in each of these towns. We can bring it even further if we want. We're at stage 3 now. Our source population is the chosen apartments from the chosen towns, and we can randomly choose a room in that apartment. And then, we have those randomly chosen rooms. As far as PowerPoint doesn't offer a great icon for room, so I just used bed. Just gotta deal with it. And then you can go even further if you want, where the source population is occupants in the chosen rooms from the chosen apartment buildings from the chosen towns, and you can randomly choose an occupant of that room. It's like, obviously these towns are gonna have different numbers of apartment buildings, and these apartment buildings will have different number of rooms. The rooms will have a different number of people. But each one is just kind of being applied like a simple random sample, or like every apartment building here has the same opportunity to be selected. At any point here, we could have done cluster sampling, where let's just say we randomly sample a town and randomly sample an apartment building in that town, and then maybe we sample like everyone in that apartment building, and then that would be like a multi-stage cluster sample basically. A stratified random sample is it's basically like solving the issue that with a simple random sample we can end up underrepresenting certain demographics. I talked about it before with that example of like a town with a really young demographic population, and although there are old people, let's just say there's like 100 old people like in a population of like I don't know, like 70,000. It's totally possible we're not going to get one old person in our sample, but that's not representative of the population because the population does have some old people. So there's something called stratified random sampling where we can ensure that these demographics that will be potentially underrepresented if we sample at random become represented. So all of my examples are very Canada centric. That's where I'm from, and yeah, I don't know. Okay, so if everyone, the entire population of Canada, I don't know what it is, if everyone has an equal probability of being sampled, it's like, I don't know if you know anything about Canada, but like basically everything north of like here, like pretty much no one lives there. Like like obviously collectively a lot of people live there, but like compared to like metropolitan hubs, yeah, like that's where most of the people would end up. That's because that's where most of the people are in the country. But if we want representation from every province and every territory, then we can do a stratified random sampling. Basically, we've separated the country into its provinces and territories, and basically you do a random sample within each stratum. A potential problem if you don't weight this though is that, like I said, almost like I'd say huge chunk of the population lives in Ontario and British Columbia, less so in these other provinces, and even less so up here. So basically, if we weight each province equally, that's not going to be representative. It wouldn't make sense if we had the same number of people in our sample from Nunavut in Northwest Territories as we did from British Columbia and Ontario, because that's not representative. It's even less representative than no people from there. So ideally, we weight the different provinces by their proportional size, so they're contributing a proportional number of people to the study, basically. So like I'm going to pick 100 because that's a nice round number. It makes it easy to explain. Where like, let's just say Ontario accounts for like 50% of Canada. I don't know what it is actually. Then you would have 50 people from Ontario randomly sampled. If Northwest Territories represents like 2% of Canada, then you'd have 2 people randomly sampled. Obviously, the numbers would be a lot bigger, but you can see how this ensures 2 things. It ensures that we guarantee representation of each of these territories, and we make sure that their representation is proportionally accurate and proportionally representative of the entire country, basically. So as far as I think, like, if I talk about the different study designs and where sampling fits into them, I think that can help bring this together, basically, because like sampling is something you often think of in like a prevalence study where you're just trying to figure out how much of the disease is there, but sampling also shows up in these different analytical observational study designs. So just starting with a cohort study, let's just say we have this big population of people. Basically, we figure out who's disease positive and then get rid of them, because in cohort studies, that's a huge part of it. I'm going to do a video of that like really soon, maybe even today, where with cohort studies, you have this like group of disease negative people that you're following over time and seeing how many develop disease in the exposure positive and negative group. But an inclusion criteria for a cohort study is that everyone started out at baseline without the disease. So that's why we took our population, identified who's diseased, and made them ineligible to be part of the sample. The next thing you do is, well, this could have come next, or it could have waited, basically, because we're sampling without regard to exposure status if we're doing like a properly random sample. But let's just say we go and find exposure status, but that still didn't have any bearing on who we chose. We still just drew a circle and kept who's in the circle. And now we have our exposure negative and our exposure positive cohort. That's sampling a cohort with like a, I don't know, like a properly random sampling. You could have also done apportionment, where basically you selectively, like, basically separate them into stratum, separate them into exposure positive and exposure negative, and randomly select so there's the same number of exposure positive and exposure negative people. And that's okay, because the only way that could introduce selection bias is if we were selecting on something that's related to both exposure and disease status, and no one has the disease yet. So the fact that we're like this is representative of the general population, because you can kind of see here that this population has more exposure negative people than exposure positive people, and that's reflected in our cohort. But if we wanted them to have the same number of people, contrary to the population at large, we could apportion them by stratifying and then picking the same number of people randomly within each strata, but making sure there's the same number that are exposure positive and negative. That's okay, basically. So for sampling case control, we're starting with that same population, identifying who's disease positive, but instead of disregarding them, we basically take them all. Because case control designs are typically with really rare diseases. That's when they thrive. And the reason that we looked for disease and took all of it is because there's probably not that many people diseased. If we took a random sample, we might not get enough diseased people to do statistical analysis. So we basically figured out who's diseased and took them all. And again, that's okay. And we're going to see why. So basically, for our comparison group, that is the main issue with case control studies, is trying to pick a proper comparison control population. So this is an example where we have like a completely enumerated population that we drew our cases from, and we can just randomly sample controls. This is nice, where now we have our case group and our control group, and we're comparing the amount of exposure in both groups. We might have more cases than is representative in the population, like if we were to, because now basically what we did was we had this population that had like this many cases and this many non-cases, and the proportion of cases in our study population is much larger, maybe even equal. And again, that's okay, because we're sampling completely irrespective of exposure status. There's definitely opportunities for selection bias to occur, but because we sampled without any information, or basically completely like unrelated to exposure is how we picked the controls in the cases, we can basically expect the cases to have some exposure distribution that we're interested in. Say we're looking at smoking and lung cancer, we basically expect this control population to have the smoking distribution of people in general, and we expect this population to have the smoking distribution of people with lung cancer. And knowing what we know about lung cancer and smoking is probably going to be higher in this group. But the fact that we chose this group purposively is not a big deal. And that'll come up more in my other videos, I guess. I'm going to do a case control one as well. This gets a little weirder if you're taking cases from like a referral hospital. But again, that'll come up in another video. Sampling in a cross-sectional study. So that's our same population here. This time we're not worried about disease or exposure yet. We're just taking a random sample, and now we have our random sample and we find exposure and disease status. So yeah, this is like the color scheme I used for my cross-sectional video, where exposure is a blue outline and disease is this yellow fill. So exposure negative, disease negative is black, just disease positive is this yellow. Just outlined in blue is exposure positive without the disease, and both blue and yellow is when you're both exposed and diseased. So we didn't look at exposure or disease status until we had our sample, basically. Non-probability sampling is another thing. Basically, like there's two. So convenience sampling is like if you're at a university, you might pick like basically your sample might be near the university, just people who are located there. There's also propulsive sampling, where basically you're like seeking out people with certain traits and sampling them. Both of these are non-probability samples. Not everyone in your source population has the same probability of being sampled. Again, it kind of depends on where you hope to draw conclusions to, because like if you just use people who live around your university's city and then try and make assumption, like try and apply those results to everyone in the country, that's not okay. But if you just want to apply those results to people who live in that area, that's fine. But basically, it's non-probability sampling because there's not a formal process involved in deciding who gets to be in the study and who doesn't. That's based on like probability. And yeah, these are uncommon and have some validity issues. Some other sampling issues, they basically all revolve around people who do participate in your study differing from those who don't. So let's just say we do random digit dialing. That's basically just like, I guess you'd put the area code in first, so you at least narrow it down to a geographic area, but then randomize the digits that follow, like the 7 digits that follow. That has some issues, possibly. If you're using the phone book, people who have landlines might differ from those who don't. Those who answer the phone in the middle of the day might differ from those who don't. They might be unemployed or retired. And also, those who agree to participate might differ from those who listen to your spiel and then say they don't want to participate, or just hang up as soon as they realize it's not someone they know. And in that way, those who participate in the study might differ from those who don't. And when that's related to the exposure or the outcome, it's basically like a form of selection bias, and it's an issue. Lastly, it would be helpful if you're able to find out how those who respond and those who don't respond differ. One way you can do that is before they hang up on you, having them specify the reason they don't want to participate, and if there's some common reason that they don't want to, then that might be helpful. You could also use those who maybe agreed but were taking a long time to do it, like you had to call a few subsequent times before they actually did the survey. You might be able to make the assumption that they share similarities to those who said no right away, and then you could use them as a proxy for non-responders to see if they differ from those who agreed to do the questionnaire and did it that day. Also, you could just use the general population. If there's any like statistics from the census about the population as a whole, you might be able to compare those in your study to see if they differ from the general population, basically.